So in the last lecture we studied branching group of instructions, and today we'll do the last group of instructions that is related to the stack group. So under this group you have 6 instructions. The first one is push RP. So what this instruction does, it saves the contents of the register pair on top of the stack. So whatever was in the register pair, there can be 4 different variations of this. Actually, leaving aside the stack group, you'll have actually only 3 different variations. So using this instruction, we can save the contents of the register pair on the top of the stack. As you know that the stack memory is also a 16-bit memory. The register pair will also be 16 bits. So we can store the contents of register pair on the top of the stack. So what will happen is at SP-1, register pair, the most significant bit of the register pair will be stored at MSP-1, and at memory location SP-2, the least significant bit of RP register pair will be stored, and the stack pointer itself will be decremented by 2 during this process, so that it actually points to the next memory location in the stack memory itself. So since register pair is internal memory of the microprocessor, it will not consume any memory. So it's a single byte instruction where the opcode will actually take up 1 byte of space. And as far as the machine cycles goes, there will be 3 machine cycles, and if you can guess, the first machine cycle is opcode fetch machine cycle. The next 2 machine cycles, what will those 2 machine cycles be? Since we are writing onto the stack memory, so we will be having 2 stack pointer related machine cycles, the memory write machine cycles. Fine. So both these 2 machine cycles will actually in one memory write machine cycle you write the most significant bit, and in the next memory write machine cycle you will write the least significant bit of the register pair onto the stack pointer. And with normal opcode fetch machine cycle, the number of T states would have been 10, but this opcode fetch machine cycle will again, whatever instruction is actually corresponding to stack pointer, all those instructions will actually have 6 T state opcode fetch machine cycle. So this is, we saw this in case of last time also. In case of branching instructions, we studied different instructions that were actually related to stack pointer. The last instruction that we studied was RSTN. It was also related to stack pointer. So wherever you have stack pointer based instructions, all of those instructions will have 6 T state opcode fetch machine cycle. So 6 T states of the opcode fetch, 3 T states each of the memory write machine cycles makes it 12 T states, and therefore an execution time of 3.84 microseconds with 3 variations. And what are those 3 variations? You will have push B, you will have push D, push H. So B is the BC register pair, D is the D register pair, and H is the HL register pair. So next you have the addressing mode. Flags actually first. No flags are affected, and addressing mode for the source and for the destination. What is the source in this case? It is the register pair. So that means the registers are the source. So you'll have register addressing mode, and the destination is the stack pointer. That is actually implied by the instruction. So implied addressing mode for the destination. As far as the machine cycles go, the micro RTL of this instruction goes, you have the opcode fetch machine cycle. So this will be your opcode fetch machine cycle. In the T4 state, push RP will be equal to 1, and in T5 and T6 states, SP will be decremented by 1. The stack pointer will be decremented by 1, so that it actually points to the location where the most significant bit of the register pair has to be written. Fine. So we saw this last time also, and as discussed there, now you'll have actually two memory write machine cycles. So one memory write machine cycle will be this. So this is your memory write machine cycle number 1, and you can see in the T1 state, SP is loaded onto the address bus. The stack pointer actually points to the stack memory location. So the stack pointer is actually decremented. So if this is your memory, this is your stack memory. So stack pointer can either point to this location, can point to this location, or can point to this location. So we are actually placing the least significant bit of the register pair in SP minus the most significant bit in SP minus 1, and the least significant bit in SP minus RPL. Fine. So in the opcode fetch machine cycle, we have already decremented SP so that it actually points to this memory location where we will store the most significant bit of the register pair. This will be RP here, not PC. This was actually last time that we had done. So RPH will go to SP, and similarly in the second machine cycle that will be having in the second machine cycles, again SPH and SPL will be loaded onto the address bus. Once the contents of the address bus are fetched, SP will be decremented. This is SP is already pointed to SP minus 2, so this will not be a part of memory write machine cycle number 2. Write will be enabled, and whatever is on the register pair, the least significant bit now RPL will now that will be loaded onto the data bus, and from data bus to the memory location. That's actually the stack pointer, because address bus is actually carrying the address that has been that actually was forwarded from the stack pointer. Fine. So you have opcode fetch machine cycle, then you have two memory write machine cycles. In memory write machine cycle number 1, RPH is loaded onto the data bus, and from data bus to the memory location, that's actually to SP minus 1. Fine. So RPH will be loaded to SP minus 1 memory location of the stack memory, and in memory write machine cycle number 2, RPL, the least significant bit of the register pair, will be loaded onto the stack pointer -2. Fine. And we do not, in memory write machine cycle number 1, SP has to be decremented. Now it's already pointed to SP -2. We do not need to decrement it further. So this is your memory write machine cycle. Fine. So you'll have opcode fetch machine cycle and then 2 memory write machine cycles. This was your first instruction, push RP. Second instruction, similar instruction, you have push PSW. So what does this do? It saves the contents of PSW. PSW is process status word on the top of stack. If I might have already told you what PSW is. It's a register pair again that actually is found by the accumulator and the flag register combined. So rest of it will be same. There's almost no difference here. So process status word is a register pair. It is formed by the accumulator and the flag register. So we actually could have combined this with push RP, but somehow this has been clubbed separately. So everything else will be same. It will be a single byte instruction. It will have 3 machine cycles. It will have 12 T states. It will have an execution time of 3.84 microseconds. Whatever was for push RP. Now there will be no variation because this is the only variation that exists for itself, and there will be no flag register will be affected. Now the source here is not a register. The source is process status word. That's actually implied by the microprocessor. That's so for the source and for the destination, both in this case the addressing mode is implied. The micro RTL will be same except for where we had actually RPL and RPH being loaded onto the data bus in machine cycle. In my memory write machine cycle 1, RPH was being loaded on to the data bus, but in this case what will be loaded onto the bus in memory write machine cycle number 1, PSWH will be loaded onto the data bus. At that time SP will be decremented by 1, and from data bus it will be moved to the memory location whose based upon whatever the address bus is carrying, and the address bus actually at that time is carrying the location stored in the stack pointer. So this will be memory write machine cycle number 1, and memory write machine cycle number 2, PSWL will be loaded onto the data bus, and from data bus to the stack pointer. So this will be the only difference between push RP and push PSW. There is no other difference, nothing else in this case. And remember, PSW, process status word, is actually a register pair formed by the combination of accumulator and flag register. Suppose to push, we will be having an instruction that will be called pop RP. Similarly, we will be having fourth instruction pop PSW. So what does this do? It retrieves the contents of So whatever was on the top of the stack, that will be retrieved and will be stored in the register pair. As far as the macro RTL now goes, as I said to you, the stack pointer basically obeys the principle of last in first out. So in the push instruction, the least significant bit was written on last, but while retrieving it, the least significant bit will be retrieved first. So whatever is on the top of the stack right now, that will be forwarded, that will be actually denoted as RPL. Whatever is below that, actually above that, MSP plus 1 will be retrieved as the most significant bit, and the stack pointer in this case will now be incremented by 2. Fine. So actually add in this was your stack memory, stack pointer minus 1, stack pointer minus 2. So the stack pointer is actually pointing to this memory location once we execute the push instruction. And once we use the pop instruction, so this data byte, that's actually the least significant bit, will be retrieved first, and this most significant bit will be retrieved next. And during this process, what else will happen? That stack pointer will start pointing back to this original memory location, that's SP. Rest of the things will be same. It will be single byte. There will be 3 machine cycles. Just remember, these 3 machine cycles are now opcode fetch and memory read machine cycles. So you will be actually having now 2 memory read machine cycles instead of memory write machine cycles, because you are actually now reading from the stack pointer and storing that onto the register pair. So there will be 10 T states of the pop instruction. There's a difference here. 3.2 microseconds of execution time, and the variations, there will be 3 variations. And as far as the examples go, you have pop B, you have pop D, you have pop H. So these instructions actually retrieve back the no flags affected and the addressing mode for the source. In this case, the source is implied by the instruction, that is actually the stack pointer in this case, and destination is the register addressing register. So you have the register addressing mode. The destination is a register pair, so the destination addressing mode will be register addressing mode. Now the opcode fetch machine cycles, the macro RTLs, you have the opcode fetch machine cycle, opcode fetch machine cycle. So what you will have in this case, you will have the normal opcode fetch machine cycle, and in the T4 state, pop RP will be equal to 1. Fine. And then you will have 2 memory read machine cycles. So in memory read machine cycle, so this will be your memory read machine cycles. So what will happen? A15 to A8 will actually be loaded with the stack pointer address. So stack pointer address will now be loaded onto the address bus once address latch enable is triggered, and the stack pointer will actually be incremented by 1. Read instruction will be enabled. So whatever was on the address bus, the contents, that will be transferred to the address data bus, and from data bus it will be transferred to not the program counter but to the register pair. Fine. So register pair L will be, it will be first transferred to RP L. So in memory read machine cycle number 2, then again the same process, SP will be incremented by 1 so that it points back to SP, and whatever is on the address bus, the contents of the address bus will be transferred to the data bus, and from data bus it will be transferred as the most significant bit onto the register pair. So this will be the micro RTL of this instruction. You have opcode fetch machine cycle and 2 memory read machine cycles. In the memory read machine cycles, in the first memory read machine cycle, the least significant bit of the data will be retrieved first and stored in the least significant bit of RP. So say for example we have pop B. B is basically refers to BC register pair. So whatever data byte will be receiving, that is the least significant bit, so it will go to C. And next, in the next memory read machine cycle, now we'll be transferring the most significant bit, and that will be transferred to B. So you have the opcode fetch machine cycles and the memory read machine cycles as shown. So for instruction number 4, as already discussed, it will be similar to pop RP except then for the name pop PSW. So it will retrieve the contents from top of stack and store in PSW register pair. So PSWL will be loaded with MSP, PSWH will be loaded with MSP plus 1, and SP will be loaded with SP plus 2. So this is your instruction pop PSW. So whatever was on the top of the stack will be retrieved and stored in the process status word. Rest of the properties similar to pop RP, single byte, 3 machine cycles, 10 T states, 3.2 microseconds. No variation here because pop PSW exists as itself. No flags affected. And as for the addressing mode goes, both source as well as destination will be implied in this case. Then you'll have the micro RTL in memory read machine cycle number 1, PSW least significant bit that will be written on to, and in next in memory read machine cycle, PSW most significant bit will be written. Next instruction, now this is different somewhat. So this instruction is XTHL. It exists as itself. Now what it does is it simply exchanges the contents of, you can guess it, contents of HL register pair with what? With the top of stack. So what happens is this is exchange. So L will be transferred to MSP, the least significant bit, and H will be transferred to SP plus 1, the most significant bit. Fine. And SP, since this is almost saying, it is almost like push and pop instruction both taking place simultaneously. So SP will be neither incremented nor decremented during this whole process. This is actually, you can say this is a combination of both push and pop being carried out by the same instruction. So at one hand it retrieves from L, and on the other hand it will send back to L. So the opcode will only consume 1 byte of data, so there is no other data byte associated with the instruction here. So you will have now 5 machine cycles. As I said to you, this is like having both push and pop together. So you have the opcode fetch machine cycle. You can have only one opcode fetch machine cycle. You'll be having but two memory read and two memory write. So we'll be having two memory read, two memory write. So memory read will be used for reading from the stack and storing to HL. Memory write will be used for reading from the HL register pair and writing onto the stack memory. Now opcode fetch machine cycle here will be again 40 states only. So 4 3 3 3 3 16 T states. G 0.32 into 16, that is 0.12 microseconds. H, you have no variation of this, it exists as itself only. So the example of this is simply XTHL. There's nothing associated with this, no flags affected. Addressing mode for the source and the destination both implied. Then the micro RTL, you have the opcode fetch machine cycle. So in opcode fetch machine cycle, what will happen is that this will be your opcode fetch machine cycle for this case. Simply in the T4 state, XTHL will become equal to 1. Now the memory read machine cycles here. This will be memory read machine cycle number 1. So what will happen in memory read machine cycle number 1? SPH will be loaded to the address bus and SP will be incremented also. Read will be enabled. AD7 will carry whatever was on the address bus. Address bus is actually carrying SP. So this is actually a memory read machine cycle. We are reading from the stack pointer and that will be written on to HL register pair. But since we have to actually also read from HL register pair, so for now what we'll do is this data will be transferred to a temporary register, that is Z. Fine. In memory write, in memory read machine cycle number 2, this data will now be written where it will be written on to a temporary register, that is W. Fine. So why we are doing this? Because if we write this data from the stack pointer onto HL register pair, HL register pair will be overwritten, but we have to read from HL register pair and store it on the top of the stack. Now the stack is actually free because whatever data was there, that has been stored now at W and Z. So in the memory write machine cycles, so this will be our memory write machine cycle. So in memory write machine cycle number 1, SPH will be again read. So now SPH is actually pointing to, since we have already incremented it twice, it is actually pointing to the top of the stack, and this data will be actually carrying the most significant bit. So whatever is in HL register pair, the most significant bit will be transferred to the data bus, and from data bus it will be carried to the address bus. Address bus is carrying the location of the stack pointer. So in short, HL register pair, the most significant bit will be written onto the stack pointer. This will take place in memory write machine cycle number 1. In memory write machine cycle number 2, again the stack pointer will be read, SP will be decremented by 1. Since we have so we are actually incrementing stack pointer in the memory read machine cycles, and we are decrementing the stack pointer in the memory write machine cycles. In short, at the end, whatever was the original location of the stack pointer, it will end up at that location only. In the memory write machine cycle number 2, the least significant bit will be now transferred from the HL register pair and written onto the data bus, and from data bus to the stack pointer. Now we are free. Now whatever was in the HL register pair, that has been written onto the stack pointer, but whatever was on stack pointer, that has been written to WZ. We need to transfer from WZ to HL register pair. So along with this, what will happen is that HL register pair will now actually carry the data that will be actually transferred from the WZ register pair. So this completes the instruction. So you have opcode fetch machine cycle, 40 states only. You have memory read machine cycle, 2 memory read machine cycles. In the second memory read machine cycle, this will not be there in this case. In particular, in this case, this is memory read machine cycle number 1. Fine. SP will be incremented by 1. It's already pointing to that location from where we need to where we'll actually store the data from H. So this is what is happening. This is your stack pointer. Stack pointer is already pointing to this location. So this location is red. Whatever was on this location, that will be stored in Z. This will be memory read machine cycle number 1. It will be incremented by 1 so that it points to this location. So whatever was on this location, it will be red and stored in W. So now we have already retrieved the contents from the stack pointer. Now whatever is in the HL register pair, first whatever is in H pair, that will be read and written to this location. So here we do not, in second memory read machine cycle, we do not need to have this. Fine, because we do not need to increment it and point at this location. We do not want that to happen. We want it to remain here only, so that we can transfer data from H and store it here. And then in the memory write machine cycle, in the first memory write machine cycle, from H we take the data and store to SP-1. SP is also decremented so that it again points to this location, and now we'll take data from L and store it here. So HL has been written onto the stack pointer. Now WZ will be transferred to HL. So W will be transferred to H actually, and Z will be transferred to L. So this will complete your XTHL instruction. Next instruction, the final instruction of the stack pointer group, is SPHL. So it loads contents of HL register pair on stack pointer. Fine. So this will be a macro RTL. SP will be carrying data that is located in the HL register pair. So this is almost similar to push RP. Push RP, we had an instruction push H. We had a variation of it that was push H. Fine. So push H, what push H does, it transfers the data from the HL register pair to the top of the stack, to the stack point top of the stack. Here the SPHL instruction, it loads the contents of HL register pair onto the stack pointer. Fine. So depending upon the instruction, it's only single byte. It will be only of one machine cycle. That will be the opcode fetch machine cycle. uh, we are not loading the stack memory with the contents of HL. We are loading the stack pointer with HL. Mind the difference here. 60 states, 1.92 microseconds, 60 states, because the opcode fetch machine cycle will now be here of 60 states. H, there will be no variation of this. I, the example is SPHL itself. J, no flag affected. K, the addressing modes. You have for the source and the destination implied. So in both cases, in this case as well as for both the source as well as the destination, the addressing mode here is implied. Finally, the micro RTL, it consists of only the opcode fetch machine cycle, and the opcode fetch machine cycle here will be of 60 states. So this is your 60 state opcode fetch machine cycle. In the T4 state, SPHL will become equal to 1. T5, T6 states, whatever was on the HL register pair, that will be transferred to SP, the stack pointer. We are not transferring that to MSP. MSP actually refers to the memory location that the stack pointer points to, but here HL directly is stored onto the stack pointer. We are not changing the contents of the memory, we are actually changing the pointer that actually points to the memory location. So that is the difference between SPHL and pop push H. Fine. So this completes our this group of instructions, and we'll actually leave the instructions here. This will be our last group of instructions. We'll do some programming, and we'll actually also start with other. We have actually some more things to cover in this syllabus, interrupts, DMA, counters, extra. So before that, we'll do some programming, and we'll start with the leftover parts of this course. So that's all for today.